I will hand over to Steve Vogel, and we are all very excited. The title of his talk is A Dilettante's Guide to FLIM-FRET. So Steve, please start.
Great, thanks. And Hauke, leave your camera on so I'll have a little bit of feedback. Visual. You can turn off the microphone if you want, but leave the camera on.
Okay.
So welcome everybody. It's a pleasure to be able to present to you virtually to all over the world, which is quite a positive thing, you know, in this time of pandemic. You know, we tend to focus on the negatives of it and the bad things that are happening, but some of the good things are, in many ways, we're more connected than we've ever been before. And so this idea that we have colleagues all over the world and we can talk to them, you know, is just a wonderful thing. On the negative side, you know, I've given a couple of these virtual talks already, and you know, the biggest negative thing, at least for me as a speaker, is that you're not getting feedback like you would in a real live talk. You know, so sometimes you feel like you're just talking to yourself, a little bit schizophrenic. So, you know, so hopefully there'll be questions afterwards and we could have more of direct exchange afterwards. So, so let me go. So Wolfgang, unfortunately, this talk won't be very much of a detective story. I'm not going to be talking about our research or, you know, what we're trying to figure out. Right before the pandemic hit, at least here in the United States, I gave a talk at a conference in Palm Springs, California, and it was much more a methodological tutorial type talk about how people can use FLIM-FRET and what it's about. And that talk was pretty successful. So I decided when I was asked to present a webinar for, you know, for this series, to do version 2 of that talk. So this is much more of a tutorial talk, and the dilettantes kind of like is telling you who my target audience is. So, you know, many of you out there who are experts in FLIM and FRET, you know, and I'm not sure you're going to gain much from this. And I'm also not trying to target people who have never heard of FLIM and FRET. What I'm trying to target is that group of people who have used it, who have read the review papers on it, but are left with questions or scratching their heads, not fully understanding what's going on, and you know, and to try to give a better understanding of what it's about. So, you know, this is an observation, right? And it has to do with something, you know, that, you know, Wolfgang alluded to, which was, you know, some of our more recent projects have ventured into the world of quantum biology, whatever that is. You know, one of the realizations, you know, when you start doing things like that is when we do FLIM experiments and FRET experiments, you know, we're using really powerful microscopes that can detect single photons, can image single molecules, can measure time on a femtosecond to picosecond scales. And this is the realm of quantum biology. This is the realm of quantum mechanics, you know, and we kind of like slowly slid into it, you know, most of us, you know, particularly from the biology background, you know, we're just doing microscopy, we're imaging cells, and nothing special. And as our capabilities got better and better, we slowly and silently slid into a new regime where the normal rules of physics may not necessarily be applying. And that's the point of this cartoon here, is that sometimes in the course of doing our experiments, we see some really strange things, and we don't understand them. Now, you know, I originally used this cartoon for a talk in quantum biology, and we're not going to talk about quantum biology in today's talk, or maybe just a little bit. But, you know, nonetheless, we see really strange things with these very powerful techniques we use, and that can be scary. And of course, my objective of this talk, this webinar, is to try to convey in an intuitive and mostly math-free way an understanding of what FLIM is about and what FRET is about. Okay, so with that introduction, let's go to this slide called the name of our game, right? So what do we do? What are they paying us for, right? And I call it the 3 B's of biology. And when I was a graduate student, the 3 B's of biology meant this: believe nothing, blame everyone, be bitter, right? But this is not the 3 B's of biology that I'm referring to here. What I'm referring to here is biology black box, right? So what we do in the most simplistic form is, you know, we have some complex biological system, this biology black box, and our goal is to try to figure out what's going on inside this black box. You know, we're trying to peer into it and figure out its mechanisms, its machinery, right? But the tool we're using is we shine light into the black box and we see what comes out of the black box, right? And in this example here, we see that the intensity changed, right? And then we use our minds to try to figure out, what does that mean? You know, we see that we have an intensity change. So what does that mean? What does that tell us about what happened in the black box? And of course, it doesn't have to be intensity change. It could be a color change, right? So this is the game we're playing. We're playing this game where we want to learn about our biological black box. We shine light into it and we see what comes out of it, right? Some of the things that come out of it, we don't normally see with our eyes. So like we can't see with our eyes phase changes or polarization changes, and we can't see lifetime changes. Our eyes cannot pick up the difference between a 3 nanosecond decay and a 2.8 nanosecond decay. They're not capable of that, of discriminating that. But just because our eyes can't see it, that doesn't mean we can't build machines that can see it. Anyway, but the important point is, for this scheme to work, you know, this scheme of this biology black box, shine light in, see what comes out, interpret that to learn about what's going on in the black box, we need to be able to measure things, you know, features of light that we don't see. And we also need, you know, if we want to interpret these changes, we need to have some understanding of how light interacts with matter. Now, you know, my background is biology. It's not physics, right? And, you know, I took a physics course, but certainly it wasn't what I was focused on. And I would say, you know, most biologists know some physics, but they're not specialized in physics. So that already sets up a dilemma. And the dilemma is, for this scheme to work, you know, this biology black box scheme, we need to know actually quite a bit about how light interacts with matter if we have any hope of interpreting these experiments. And on the other hand, this is not the field, our comfort zone. So that sets up a dilemma. Okay, so let's talk a little bit about FLIM, fluorescence lifetime imaging. So in the upper left corner here, I show you some of our old data when we first started doing FLIM, maybe 17 or 18 years ago now. And we were using it for FRET, and we're going to get to that in a second. But here, you know, the blue curve is a lifetime decay curve of cerulean, a blue fluorescent protein. And the red one is a cerulean that's been ligated to a Venus, a yellow one, that's undergoing FRET. And you can see that both of these are decaying, right? So what is a lifetime? What's it about? Well, let's just focus on the blue one for now, right? So we can see on this semi-log plot that the decay is pretty linear, right? And it, you know, and it starts, this is normalized data, so it's starting at 1, you know, and it's decaying, right? And this observation was made a long, long time ago, and people wanted to understand, what does it mean? The same way as we want to understand what's going on in the biology black box, right? And on the bottom are 3 pictures of 3 scientists who devoted large segments of their careers to trying to understand what is the fundamental mechanisms that's responsible for this decay. And this is Jablonski and the Perrins Jean-Baptiste, who is the father, and his son, Francis. Jean-Baptiste actually won a Nobel Prize for confirming Einstein's predictions of, of Brownian motion. Right? Okay, all of them were living in a period where quantum mechanics was this newfound science in the 1920s, and they were reframing things, and they were all kind of like really interested in, can we understand this decay of this fluorescent signal in terms of quantum mechanics? And long story short, it ended up in this kind of diagram shown on the right, the Jablonski-Perrin diagram, which involves, where you have a molecule, let's say of cerulean, in its ground state, and there's many vibrational modes of that ground state, and then you shine light on it, and you have a quantal change up to an elevated state, and there's many vibrational modes of that, but those rapidly decay into the most stable S1 state, and then from there, this thing can decay back down, shown here, and if it decays back down, it emits a photon, right? So this is a scheme that they worked out for understanding this, right? And this scheme then begs the question, okay, how long does the energy hang out here at this lowest level of S1 before it goes back to the ground state and emits a photon, right? Well, a lifetime, a fluorescence lifetime, in fact, is the average time that one of these molecules spends in this S1 ground state. That average time is what we call a lifetime, right? And that's what they're studying, and that's what we're using with this technology. Okay, and you can note, shown here in red, that this is already a strange mixture of classical physics, i.e. rates and kinetics and stuff like that, and quantum mechanics. In other words, it could jump from here to here, but it can't jump from here to halfway between here. This is a quantum phenomenon. Okay, so how do you measure FLIM, right? Well, the short answer is we buy a nice machine from Wolfgang or from one of his competitors, and we let the machine do it. But it is actually useful to have some understanding of the fundamentals of what's going on. And so what I'm showing here, tagged A here, is, a pulsed laser excitation. This is modeled after a Ti-sapphire laser running at 80 megahertz. So what that actually means is that every 12.5 nanoseconds, we're going to have a laser pulse hitting our sample, right? And that sample could be biological, it could be anything. So then what happens when it's hitting something that might have fluorophores in it? Well, every now and then, you'll detect a photon of fluorescence coming out of your sample. And in this case, I'm showing you that 3 of these yellow spikes, 3 yellow photons were detected. In reality, so these 3 were detected. This was a failure. This was a failure. Nothing detected here. Nothing detected here. Nothing detected here. So this laser pulse, and this laser pulse resulted in this photon, that photon, and that photon. In reality, it's actually much less efficient than depicted here. I mean, here it's 3 out of 1, 2, 3, 4. Here it's 3 out of 8. In practice, at least in my lab, we're typically detecting 1 photon for every 400 to 600 laser pulses, right? But this is to illustrate it. This is for educational purposes. Okay, so once you detect these photons, then you can see in these dashed red lines that you can measure a delta time. That delta time is the time from the laser pulse and when the photon is detected. And actually, even that's not true. In reality, the delta time is measured from when the photon is detected until the next laser pulse is. And then because you know what this time is, you can subtract that from it, and then you can calculate what this is. But that's not important. What's important is you end up with these delta times. So in this case, the time between this laser pulse and when this photon was detected was 3.16 nanoseconds. In this case, it was 8.84 nanoseconds. In this case, it was 1.96 nanoseconds. Okay, so if we do this, let's say 10,000 times, we can get a lot of delta times. And this is depicted here. This was from a Monte Carlo simulation I ran. You know, so this is a Monte Carlo simulation, I believe, of a sample that should have a 3 nanosecond decay, right? And what you can see is, again, on the x-axis is just the 10,000, is it 10? Yeah, 10,000 photons that we detected, the 10,000 delta times we detected. And on the y-axis is what that delta time value was. Once we have this kind of data, and when I say we, it's not really we, it's the machinery we use, can then take this data set and turn it into a histogram. And when you do that, you get this histogram shown in blue. And that is now showing you the decay of your lifetime. Each individual event is not a decay. It's a single event. It's one photon emitted per time. But when you look at the ensemble behavior, either of one molecule over and over again, or thousands of molecules measured once, or any combination of those, that's when the lifetime emerges. And shown here, you can fit that decay, this blue histogram here, to a exponential fit using many, many different softwares. You know, we like Igor Pro in our lab, so that's what was used here. And when you see this, you can see we fit a tau, a time constant of 3. It doesn't even say nanoseconds, it is nanoseconds, right? So this is essentially how the machinery that we use for FLIM works. This is a this is a time domain machinery. But there's other techniques using frequency domain, street cameras, etc. I'm not going to talk about those other approaches. Okay, so that's how you measure a lifetime. And it sounds kind of complicated, and the engineering is remarkable, but in practical senses going into the laboratory, it's pretty straightforward. It's pretty easy. Okay, so now that you've measured a lifetime, like in this case, the cerulean alone or the cerulean Venus, what do you do with it? How do you parameterize it, right? So, okay, I measured something, I'm excited, but how do I call up my friends and tell them this is what I found? You know, other than just saying, well, it's going down with time, right? You know, you need a way to parameterize it, right? And the way that most people parameterize it is by doing curve fitting, and you fit it to mathematical models. And usually these are either single exponential decay models or double exponential decay model, and some people have done triple, and there's other variants as well, right? And the objective here is to try to find a model that does match the decay that you're actually observing. So what's the big deal about taus? And this is a confusing thing, particularly for people who are not comfortable with the mathematics and, you know, the idea of what is a time constant, you know, what's the big deal about taus, right? So one of the big deals about taus for a single exponential decay is the tau. So again, this is single, look at this equation, single exponential decay. Here's the tau, right? So when you do a fit to this, you'll get a number for tau. As I showed you before in that histogram, the number that I got was 3, and that's a very typical 3 nanoseconds. It turns out that the area under the decay curve, shown here in light blue, is directly proportional to the value of tau. Okay, so that again is a mathematical term. Does it really help you? You know, let's say as a biologist, okay, so the area under the curve, that's even more confusing, you know, mathematically. But again, let's look at this. This is normalized photon counts. This is time. So the area under this curve is essentially how many photons were given off. In this case, it's a normalized photon count, so it's relatively speaking. So imagine if you're thinking about the blue curve or the red curve here, the areas under these two curves will be different. It'll be smaller for the red curve than for the blue curve. And that tau value or tau average value is going to be directly proportional to how many photons were given off. And as biologists, that's actually the real number we want. We don't care a hoot about taus. What we really care about is how many photons are being given off. Okay. Why do things decay exponentially or not, right? Okay. I mean, clearly these are decaying exponentially, but do they have to? Is there some rule written somewhere that all things must decay, exponentially? And the answer is not really, right? But when things do decay exponentially, it has a meaning. And what that meaning is that it's saying that in this case, we excite the molecule, it ends up at the lowest level of S1, and now every unit time, it has a certain probability of emitting a photon and going back to its ground state. If that probability does not change with time, if it is constant, right? So in other words, at time equals, 1 here, it might not go, it might fail. It's a probability, right? So, let's say it has a 50% chance of going down. We're saying if it failed at 1, at time 2, it's going to have that same 50% probability. At time 3, it's going to have that same 50% probability. If a system behaves that way, it decays with a single exponential. If that probability changes with time, it will not. Similarly, for simplicity, we like to think of our systems as having only one thing in them, and so we only worry about its one decay probability. But in practicality, some fluorophores might have more than one excited state, or some of our samples might have more than one fluorophore. And so you could see what looks like much more complicated decays, and you have to keep that in thought. Anyway, so that's why things decay exponentially, and sometimes they don't. Okay. So now, if you want to interpret FLIM, you also have to understand, well, what can influence these things? Let's say I have a very ideal system that normally does decay with a single exponential. And so it goes up to this excited state. The point that you have to think about is anything that can happen when it's at its excited state, any other pathway besides giving off a photon can influence the rate that it gives off. So if you're having transfer of that energy, let's say in this case to a triplet state, that's going to influence your lifetime. Anything that happens in the excited state, quenching, collisional quenching, whatever, can all influence that lifetime. So environmental factors can influence the lifetime you measure, and in many FLIM experiments, that's the main thing you're interested in, is what are the environmental factors that are changing the lifetime. In FRET experiments, you are hoping that there are no environmental factors that are changing the lifetime other than this FRET phenomenon. So now we can transition into FRET. Okay, this is a figure from a recent review paper I had, so it's a shameless plug for our review paper, but it's trying to get to the main reasons why we think people use FRET. And it's shown in that kind of like green box all the way on the right, applications of FRET. So what is FRET? It stands for Förster's resonance energy transfer. And it's a physical phenomena where you excite one molecule, one fluorophore, and under certain conditions, it'll transfer its energy to a nearby molecule. And that phenomena, it is usually based on the distance separating those two molecules. And that's what most biologists are interested in. That's not always true, right? So nonetheless, this technique can be used for binding studies. It can be used to study conformational changes in proteins, dynamic studies, assays, biosensors. There's many, many useful biological applications that use this FRET phenomena. And what's unique about this FRET phenomena is depicted in the main panel here. So if you go all the way to the right, you see this red ellipsoid, that's supposed to represent what is the volume that a normal, let's say, confocal or 2-photon microscope is interrogating in terms of fluorophores. And you can see this itty bitty little spot here, and that little spot is drawn to scale to the whole volume. That represents like 1 GFP molecule. So it gives you an idea that when we use, let's say, 2-photon microscopy, you know, many GFPs might be able to fit into this spot, right? A matter of fact, the number is about 2.7 million can fit into this spot, right? So if you think simplistically like a co-localization experiment, let's say I have my 2-photon microscope and I see some green fluorescence and I see some red fluorescence, and they're both coming from the same pixel, the same spot, right? You know, so it's telling me there's co-localization. But in the worst case scenario, given the fact that 2.7 million GFPs could fit into here, what it's telling me is that at least one of the 2.7 million that could be in there was red, and at least one of the 2.7 million that could be in there were green. It doesn't mean that they're interacting with each other. It just means that both of them are in the same spot. Now we can move over to the blue ellipsoid. That's representative of super resolution microscopy. And you can see things got a lot better. The resolution is much higher than here. So the volume, you know, I mean, it looks like the volume's the same, but in fact, the volume's much smaller. And you can get a sense for that because now you could actually see that spot in the middle representing 1 GFP molecule. And in this scale, about 485 GFP molecules can fit into the volume that's interrogated by super resolution microscopy. So that's a much better case, right? In other words, if you did co-localization with super resolution, now instead of being 2 out of 2.7 million possible molecules, now it's 2 out of 485. It's not so bad. But now you go over to the green spheres, which represent FRET, and it represents very weak FRET at the 10 nanometer diameter, intermediate FRET at like the 6.5 nanometer diameter, and very strong FRET at the 3 nanometer. And you can see that now we're talking about, you know, 200 GFPs fitting in, or 50, or down to 5 or even less. And because of this reduction in the volume, the meaning is the same. But I'll stress over and over again, even when you do a FRET experiment, let's say you detect, you know, a red molecule that was here on the surface of the sphere, it does not mean that these molecules are interacting with each other. It just means they're within a certain proximity of each other. Okay. So strange things can happen when fluorophores get close. So this is a picture of Förster, who FRET is named after, as a young student doing quantum mechanics. And in the bottom, I have 2 yellow fluorescent proteins. And you can see that when you bring them together, some strange things can happen. This figure, you know, has been modified, but it comes from a paper from 1965 of Förster's, where he's talking about different coupling regimes. And this is actually the only part of this talk that I'll even talk in any way about quantum biology. But the main point is saying that when fluorophores get close together, they can be strongly coupled. And the degree of that coupling determines what kind of strange things are seen. This box over here with the dashed red line, that's the weakest coupling regime for this strange interactions. And that's the regime, that's the box where we see FRET, what we were just talking about. There are other regimes over here and over here. They fall into the category of coherent energy transfer, and much stranger things happen there. And I'm going to leave it at that. You know, we're really interested in these strange things, but that's not the subject. We're interested today, at least, in the FRET regime. So what's strange about FRET? What happens in FRET, and I already mentioned it earlier, is we can excite, let's say, this yellow fluorophore, and if we have the right techniques for following it, we might notice that even though we excited this one might be the one that gives off the photon. That's pretty strange behavior, right? We excited this one, but this one gives it off, right? And the reason why that works in FRET is because we excite this one, but then because of this FRET reaction, this molecule can give the energy to this molecule. It goes back to its ground state. This one gets elevated, and now this one gives off the photon. That is the FRET phenomenon, right? And that's what we're talking about here today. Okay, FRET is a non-radiative thing. So when one of those molecules gives energy to the other, it's not because it's giving off a photon and the other molecule is catching it. It's that they're having a resonant interaction between them and the energy is being transferred. It's analogous to, we could hit a tuning fork, you know, let's say tune to A440, and we can hear, you know, we hold it up in the air and we could hear that A. And now if we touch that tuning fork to a guitar, now all of a sudden the guitar will start resonating at 440, and we'll see an A coming out of the guitar instead of out of the tuning fork. The energy from the tuning fork has been resonantly transferred to the guitar. That's analogous to what's happening with FRET. So it does not involve photons, it's non-radiative, okay. Also, it's important to realize that FRET occurs in the near field. So these are distances less than the wavelength of light. So for example, a typical white light FRET reaction might use 500 nanometers of light. The transfer of energy that we're seeing is always less than 500 nanometers of light. It's less than one wavelength. That's near field. And in fact, it's much less than one wavelength. So typically when FRET is happening, even though the light might be 500 nanometers, the largest distances that we see this FRET transfer is typically 10 nanometers or less. So it's much less than the wavelength of light. Okay, so here again is another cartoon to explain heterofret, the kind of FRET that most of us think about. We have a blue, let's say cerulean, and a yellow, which is a Venus. And if the two molecules are far apart, we excite the blue and it emits a blue photon. But if we bring them closer together, then we can excite the blue, it can give the energy to the yellow, and the yellow will give off and will detect a yellow photon. And as you can see in the middle of this slide, there are many, many ways that people have devised to follow this FRET reaction. But what we're talking about today is changes in the donor lifetime, right? And using changes in the donor lifetime, so in other words, using FLIM to detect these changes. But again, I'll remind you, there are many other ways. The one, in my opinion, great advantage of using donor lifetime is it's giving you, in addition to an idea of how much energy is being transferred, you know, what is the probability of that transfer? Additionally, it also gives you kinetic information of how fast that energy is being transferred, while almost all of these other techniques do not tell you about the kinetics of transfer. Okay, how do you parameterize FRET? You know, we talked about how do you parameterize FLIM. What do you do with FRET? I measured some FRET. I'm excited. I want to tell my friend about it. How am I going to tell him about how much FRET we had? So again, here's another cartoon. Here's a donor. We excite it. It gives off light. You can think about that the rate that it gives off the light, K fluorescence, is equal to 1 over the lifetime of that molecule, right? So that's, you know, even though we talk about it as a tau, if you just take the inverse of that tau, that inverse is a rate. It's the rate of photons coming out of this molecule, right? Okay, then we could bring an acceptor to be close to it, usually less, as I said, less than 10 nanometers from it. And if we do that, now we introduce a new rate, a FRET rate, right? This old rate is still here. We haven't gotten rid of that. We've just introduced a new rate, right? Now that we have two rates, you have competing pathways. And those competing pathways is what we're interested in. And that's what we want to tell people about. And essentially, the way that you parameterize FRET is typically called the FRET efficiency, which is the fraction of excitation events that transfer energy by non-radiative dipole-dipole interaction mechanisms to an acceptor, right? So what is this? What this number is saying every time I excite this donor, when I have an acceptor close to it, what fraction of the time will the energy go here as compared to going here or anywhere else? That's the number we're interested in to parameterize it, right? So it's a probability, right? In other words, if I don't have the acceptor there, then there is no probability of going to the acceptor. 100% of the time, it's going to go somewhere else. But the second I introduce that acceptor, now some of the times when I excite the donor, some of that energy is going to go to the acceptor, and I want to know how often that happens. And you can see on the right, this symbol E. So E stands for FRET efficiency. And you can see there's many different equations that have been used to estimate FRET efficiency. And they're all actually variants of each other. But when you're doing FLIM-FRET, this is the equation you're using. So the FRET efficiency is equal to 1 minus tau donor in the presence of acceptor over tau of the donor alone, right? Okay. Again, keep in mind, we're not interested really in the tau per se. We're interested in the fact that it represents how many photons are being emitted, right? So if you just take this tau donor acceptor over tau d, what that means is tau dA is going to be how many photons are emitted by my donor when I have an acceptor present, and tau d is when I don't, so that's the 100%. And so that ratio, tau dA over tau d, that tells me essentially what fraction of events result in the donor giving off a photon, right? And then by going 1 minus that, that tells me what fraction went to the acceptor, which is what we're interested in. So mathematically, it has taus and stuff in it, but the reality is it's very simple algebra. Okay, so here's a FLIM-FRET, the same data I showed you before, single exponential, double exponential. Okay, here's the equation I told you. So we can do curve fitting on these curves. So we can fit the blue curve, and just looking at it, I know we can fit it really well with a single exponential decay model, which is this one. And this red curve, because it's a semi-log plot, it's not a straight line. So I know just looking at it, there's no way this could be fit to a single exponential model, right? So we're going to have to do at least a double exponential model or more. And in practicality, it's well fit to a double exponential model. And once we do that, we can get taus. Certainly we can get a tau for the blue, but what do we do if we need to use this multi-exponential decay? How do we deal with that, right? So, again, what are we really interested in? What we're really interested in is the area under the curve. We don't give a hoot about taus. What we care about is what is the area under the curve, because the area under the curve is going to tell us the relative amounts of photons that are given out when we have the donor in the presence of an acceptor, all right? So again, for a single exponential, tau itself represents the area under the curve. What about for a multi-exponential decay? So it turns out there's a thing, instead of measuring tau, you can measure average tau, and it's actually called the amplitude-weighted average tau. So if you wanted to calculate the average tau, again, you would say amplitude 1 of the first decay component times tau 1 of the first component plus amplitude 2 of the second component times tau 2 of the second component divided by A1 plus A2 will give you the amplitude weighted tau. And that number is in fact proportional to the area under that red curve. That's what you're interested in. You don't care about taus. You care about what is the area under the curve. And so an interesting thing is, we put a lot of effort into fitting taus and fitting curves, but we could just as easily integrate the area under these curves and come up with the same answers. It's the exact same thing. Okay, so do we need taus? No, we don't need taus. Taus is a useful tool for calculating the area under the curve. And its origins go back from the days before home computers were everywhere, ubiquitous, and it was actually hard to integrate the area under a curve. So mathematicians looked for tricks to make it easier. And one of the tricks that made it easier was using taus, right? But in fact, what you're really interested in is what is the area under this curve versus what is the area under that curve. That's what you're interested in. Taus are just one way of doing it. Okay, so what do you need for FRET? In most review papers, it'll list three things: close proximity, overlap of donors, permissive dipoles. We're going to go with that. I list a fourth thing called fluorophores act independently. I'm not going to talk more about that, but this goes into that figure of Förster's, which is saying that if they act independently, then you could be in the FRET regime. When they cease to act independently, now you're in those strange areas of coherent energy transfer, and that's a different ballpark, but we're not going to talk about it. But we are going to talk about these three real quickly. So, close proximity. So this is a figure showing distance normalized by the Förster distance versus a FRET efficiency you measure. And you can see that there's actually two curves, even though in most review papers, you'll only see the dashed blue curve and you'll never see the red curve. And basically what it's saying is that the relationship between distance and FRET efficiency is not written in stone. It actually depends on how fast your fluorophore is moving and rotating in space. And the extremes of that is the dynamic regime, which is this blue, and the static regime, which is this red, right? And of course, you could have things in between, and that would be in between these two curves, right? But the vast majority of FRET theory and papers only talk about the dynamic regime. And so you'll see this equation, but you'll almost never see this equation, right? So is this important? Why is it important? Actually, we think it's very important, right? But before we'll go into that in a slide, I think it's the next slide or one after that. But first, let's talk about distance. So imagine we'll do a thought experiment where we have a donor and we have an acceptor and we express it in a cell, right? So the thought experiment is, at what concentration of acceptor is it so high that one acceptor will always be within 10 nanometers of another acceptor? Well, you can actually calculate that for things that are soluble in 3D space. That's shown by these two curves. These are two closely related equations for calculating it. So this is the one that I first saw, but actually after comparing the results with experimental results with FRET, I actually believe this bottom green curve is the more accurate curve for these estimates. So what does it say? Well, what it says is that if you have an acceptor at a concentration of about 200 micromolar, the average distance between acceptors are going to be 10 nanometers, right? So now imagine if you have that and you plop in a donor in that same solution, right? That donor is always going to be within 10 nanometers of acceptor, not because it's binding to it, but because it can't escape it. It's everywhere. It's like putting one person into a crowded elevator with other people. Of course it's going to be close to those other people. It's not because they're married to any of those people. They're just stuck in an elevator together, right? Same thing with molecules in solution. So if you're working at concentrations above like 200 micromolar, everything is going to be fretting with each other. Not because they're binding to each other, just because they're fretting. So it's important to work at low concentrations to avoid this artifact. Okay, this is the overlap of donors and acceptors. So again, this is showing cerulean and Venus. Dashed line is the absorption, blue line is the emission, dashed line is the absorption of Venus, solid line is its emission. What we're talking about is the overlap of the emission of the donor, so that's the solid blue line, and the absorption of the acceptor, which is this dashed yellow line. And you can see there's a lot of overlap between those two. That overlap, the reason why it's important is actually quantum mechanical. What it says is that these two transitions, that is the transition of the donor down to the ground state and the transition of the acceptor from the ground state up to its excited state, share the exact same energy. And the overlap integral is giving you an idea of what is the probability of finding two molecules that will have the same transition energy, because only under those conditions can you have this FRET phenomenon. It has nothing to do with emitting or absorbing photons. And then finally, the most confusing is this permissive dipole. So permissive dipole is this kappa squared. This is where most people's eyes glaze over and they just shut down, because anytime you have an equation with a cosine or a trig function in it, people don't like it. And it's unfortunate, but it is a reality. So again, I'm not going to go too much into detail here, but the main point is you have this blue arrow here. That's the direction of the emission dipole of your donor. And then you have these yellow arrows, which is the position and direction of your absorption dipole of your acceptor. And they can be changed in two ways. In this case, which are changes of where in space relative to the donor can you place the acceptor. You could place it here on the equator, you could place it here at the pole, you could place it here somewhere in between. Right? This would be the same value regardless where it is along that meridian, right? The other thing is this donor sets up an electric field, and that electric field has to be sensed by the acceptor. And so you can see these electric field lines are not uniform in space, but for the acceptor to be able to detect the electric field, it can't be perpendicular to the electric field at the position it's in. So for example, this molecule here is perpendicular. It cannot sense the electric field. This molecule is perpendicular to the electric field here. It cannot sense it. But this one can, and this one can, and this one can. And the ability to detect it is going to be a function of this angle. And so again, it's useful to understand this equation, but it's not essential. What's more interesting, however, is you can say, given that you have randomly placed donors relative to acceptors in a population, and you have random orientations at the location, that's called isotropic, what will be the value of kappa squared? And so that's this distribution here in green. This is the probability distribution of kappa squared for an isotropic population. And you can see that you can have kappa squared values ranging from 0 to 4, where 0 is the most likely kappa squared value you'll have, and 4 is the least likely value you have. It turns out, however, that if you want to have good FRET, 4 will give you the best FRET, and 0 will give you no FRET. Right? And this is not a Gaussian distribution. It's not even close to a Gaussian distribution. This is a really strange shaped distribution. But it turns out that the average value of this distribution is 2/3. And that's a very famous number in the FRET community, because you'll read in 99% of the papers you read on FRET, there'll be some sentence that goes, assuming kappa squared is 2/3, the distance is blah, 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 right? And the reason 2/3 is assumed often is the idea that if these molecules are moving real fast relative to the lifetime of the donor, then it'll assume many orientations, and the average orientation will be indicative of 2/3. Okay. So now I'm going to show you some examples of how this might be important or not, right? So in the early days of FRET, no one worried about this kappa squared, everyone assumed it was 2/3 and everything was good. And that was a perfectly fair assumption because of this dynamic thing. So I have this cartoon here of two organic dyes. You can think of it as fluorescine and rhodamine. And you have no FRET, so the distance is 2 times the Förster distance, and FRET, which is the distance, is the Förster distance. And then you can run simulations of what the lifetime will be. So in this case, in the Monte Carlo simulation, I set it up to be a 3 nanosecond decay. And when I set the distance to be 2 times R0, we see a nice single exponential decay, and we can fit it. And the fit gives us 2.97. So that's essentially saying that it's almost no FRET, just a little bit, right, at that distance. On the other hand, if the Förster distance is the same, the separation is the same as the Förster distance, now we see when we do the fitting, it's still a single exponential decay, but that single exponential decay is now 1.5. Okay, so, how would, if we just took this data and we wanted to measure FRET, we would say, okay, 1.5, divided by 3 and 1 minus that, and that would say 50% FRET efficiency. Okay, and that's true, and it's perfectly legitimate, right? And then, however, people started thinking about more complex analysis. So you could imagine the scenario, do a thought experiment. What would happen if half of my molecules had a separation distance of 2 times R0, and the other half of my molecules had a separation distance that was equal to R0, right? And I did an analysis. Well, under these conditions, what I would see would be a double exponential decay. I can fit it to this double exponential decay model. And the amplitudes would, so tau 1 would be, 1.5, and tau 2 would be, this 2.97. And the relative amplitudes would tell me how much of each one is there in my sample. And if it was 50-50, then this would be 0.5 and that would be 0.5 and everything would be great, right? And that's all true. The problem is when this theory was worked out, fluorescent proteins hadn't been discovered yet. And the theory of most of this had not been worked out either. So here's fluorescent proteins. And fluorescent proteins, unlike organic dyes, they don't move fast. They rotate very slowly. So you cannot assume that kappa squared is going to be 2/3, right? You can assume that it's isotropic under certain circumstances, but you cannot assume it's 2/3. So in the case where you have very, very weak FRET at 2 times R0, again, it's decaying as a single exponential. It's well fit to a single exponential. And again, here we measure 2.966. It's the same number mathematically, right? No difference between this and this. But now what happens in this case? And what happens is it's not a single exponential decay anymore. It's a much more complicated decay, right? It turns out, you can see with the dashed line, this is a double exponential decay fit, and it's actually a really good fit, except for at this very bottom part here, right? But this bottom part here, because this is a log scale, represents less than 1% of the total data, right? So this is a really good fit, but it's not really what's going on here. And you can see that we have A1, A2, we have a tau of 2.49, a tau of 1, so this leads to endless confusion of people trying to do FLIM-FRET experiments because they're trying to understand what the heck does this mean? And all of this arises from the fact that kappa squared is not 2/3 when you're doing fluorescent proteins, and you can't assume that it's 2/3. And so you're going to have much more complicated things. And because of those complicated things, this idea of fitting it to a double exponential and then interpreting it in terms of amplitude 1 and amplitude 2 falls apart, right? And can't really be applied here. Now, the good news, however, is if you do a fit, and it's a good fit, and in fact, this is a very good fit, what it means is your tau average that we talked about earlier will be very accurate. And if your tau average is accurate and you plug it into the FRET equations, that means your average FRET efficiency will also be accurate. So you can accurately measure how much FRET you have, but it's very difficult to interpret it in terms of this simplistic model of what it means. So we're almost finished here. So, so again, interpreting FRET is challenging because there's many factors that can influence it. As biologists, we want to interpret it in terms of, in terms of separation distance. But in fact, if something changes the overlap integral, or changes the absorption coefficient of the acceptor, or changes the wavelength of overlap, or changes the dipole orientation, or changes quantum, there's many factors that can influence the FRET. Ideally, when we're doing a biological experiment, we want all of these factors to be frozen and this be the only floating non-controlled variable, and therefore that's how we interpret our results. Unfortunately, sometimes when we do these experiments, we can't assume that these things are frozen, and that also leads to complexities in trying to analyze our data. So what are the problems? Introducing fluorophores might perturb biological systems. Polarization artifacts, refractive index artifacts. FRET can change as the donor-acceptor ratio changes. Cell targeting trafficking artifacts, fixation artifacts, autofluorescence, photobleaching. There's so many potential problems that you have to be careful. And this is not new, So on one hand, people who do a field are trying to sell people in its virtues, and we tend to gloss over the problems. But there are problems, and you have to deal with these problems. But the good news are there's many kinds of control experiments that you can do to deal with these things. I'm not going to go through them here, but there, in our papers and other papers, there's lots of talks about the many controls you can do to help you interpret your data. And now I'm going to go to the last slide, which is the takeaway message and the point of this. And the main point I want you to leave here today is saying, measuring FRET with FLIM accurately and with precision is actually relatively easy to do. And that's a really good thing, and it's a really powerful thing. Interpreting FRET measurements is much more complicated, and you have to be very thoughtful, right? Because there are other factors that could make it much more confounding, and that's why we have to learn about what are these things that could lead us astray. So with that done, I'm happy to open it up to questions.